until the university takes shall we get started? Okay, so we're going to get started. It's my pleasure to introduce Kwok and Barrett. Kwok is a scientist at Google Brain. He did some of the actually pioneering work in deep learning with Andrew Ng in his PhD, and then went to Google and has done lots of really exciting stuff since then, some of which he'll tell us about today. And then Barrett is currently a Google Brain resident, so he's in the residency program, and finished his bachelor's at USC.
Yeah, thank you, Sergey. Is the microphone working? Okay, cool. So hi, everybody. My name is Kwok. I'm here to present some of the work that we do in using machine learning to automate machine learning. I'm going to do the first half of the talk, and Barrett is going to do the second half of the talk. And feel free to interrupt at any point in the during the lecture. We don't have a lot of slides, so interrupt as much as you want. So this is, again, John worked with many colleagues at Google Brain in Mountain View. So what's the motivation of the work that we do? If anybody, I guess that some of you are familiar with neural networks, and if you work with neural networks, there's this problem is that like, every time you work with it, you have to deal with a lot of hyperparameters, and they have to design structure of the neural network. Currently, we have to spend a lot of efforts. Even at Google Brain and at Google, we spend a lot of time tuning neural networks. And this is something that is not easy to do. We have to hire people who have PhDs, who have actually have very good intuition about the domain to design neural networks. And the way I see it is that back when I started doing machine learning, there's shift features and hawk features and so on for computer vision. So people hand engineer features. And now the paradigm shift is from going from feature engineering to neural network engineering. What we want, our main research question is, can we automatically do this? Can we have a way to learn good architectures automatically? Just to give you some values of designing better neural networks. So if you look at the ImageNet contest, it started out in 2012 and AlexNet won the contest. But as time progresses, people get better and better at designing neural networks, and better neural networks give you better values, better accuracy. So right now, the best network is Inception V4, and it's fairly complicated. So if you look into Inception V4, it consists of a lot of cells, and inside each cells, you have several blocks. Not only it's complicated to select what the structure of the block, but how to connect them up as well. And it matters a lot. Just to be more specific, so if you work with computer vision, and if you take a class in computer vision, you see this a lot, is that these days people work with convolutional architectures. This is the picture of AlexNet, published in 2012. And the way it works is that you give the network an image, and then you have to perform some sort of convolution. Right? You decide the size of the filters and how many filters you have, and you do first set of convolution, and then you feed it into the next layer to do max pooling. And then you feed it into the next layer, and then you decide how many filters and the size of filters, and etc. Right? And here we have 5 convolutional layers, and then you have 1,000 way softmax and 3 fully connected layers. So the decision that the architect, the guy who designed the network has to make is how many filters you have, how many layers you have, how to connect them up, and what the size of filters, and etc. So that's people do a lot in computer vision. And if you in a time series analysis or in NLP, people do People use recurrent networks a lot. And you can start out with a very simple architecture, like a standard recurrent network, by basically taking the hidden state of the previous step, and then taking the input of the current step, do some kind of interpolation, and then apply a 10-hash activation function on every dimension, and then that's the hidden state of the next step. Now, that's simple, but if you use something called the LSTM, a long short-term memory network by Hochreiter and Schmidt-Huber, you get better result. And I won't go into details, but there's more gating function and there's more complexity going into this box. There's a lot of function that you have to learn in order to give rise to the hidden state. And that matters a lot. And this is, if you use Google Translate today, you basically interact with one of such networks. It's called the LSTM cell. Is there any question so far? Okay. Together with Barrett, we built this framework called Neural Architecture Search. And it uses reinforcement learning to design architectures. And the key idea is the following. The first insight is that even though neural networks can be very complicated, the structure and the connectivity of a neural network can be specified by a string. So if you work with a cafe, for example, right, you have to specify whether it's Inception or is it AlexNet and so on. And it's actually the way these people specify is actually a string. For example, here's a following string. This is a very simple string. Is that you can say filter width is 5, filter height is 3, and number of filters is 24. That's specifying the configuration of one layer. And then you can specify a configuration on another layer, and etc. And then you can specify how to connect them. I'm going to go into details about that later. And that's a key insight. And the second insight is that we're going to use a recurrent network to generate such string. Because recurrent network is very good for generating text. So we can use a recurrent network to generate string, one token at a time. And then how do you going to train this recurrent network? Well, to train this recurrent network, what we do is that we use reinforcement learning in the following manner. So it started out, the RNN, the controller, want to start out sample a string. We're going to get that string, and then we're going to construct a neural network according to that string. And then we're going to train that recurrent network to convergence. And then at convergence, we're going to get some accuracy for that string. And then we would use that reward signal, which is the accuracy, to actually use and reinforcement learning to train the recurrent network. So the recurrent network over time will improve its ability to sample better and better strings. Okay, now I can take questions. This is the most complicated slide.
So what's the state of this controller network that it specifies? I mean, do you like do summary statistics on the data set, or depending on your loading problem, like what features do you use to specify this RNN that then generates a neural network? I go to that in a minute. So I take this question.
I was just wondering, are tools like, so there's tools like Bayesian optimization, which are also basically doing active learning or RL, or there's this algorithm called hyperband. What's the benefit of actually parameterizing the structure by like a string as opposed to just saying filter width can be an integer from like 1 to 100 and then treating it in some other RL framework?
So the first advantage of using an IO is more flexible. So you can have a variable length strings. Okay. Right, and you can have variable depth, or all kind of connections.
Okay, I see.
Right, so that's very powerful because neural network you can't just like select ahead of time the length.
So the RNN would actually output a termination token? When
We didn't do that, but that's our goal. Right.
So it's like a more flexible.
More flexible scheme to do it. Yeah.
And so in some neural networks are just like plain feed forward, whereas others might have different like branches that go to different parts of the output, or potentially combine like a ResNet.
Yeah.
If it's so with the string, you like kind of have the serial ordering.
Yeah.
In other cases, would it be harder to use a string representation if you had like kind of a string?
So I will go to the part where we have connectivity, doing skip connection and stuff like that in a little bit. Okay. So let me go to like the framework in general for now, so that people have a high-level picture of what's going on. Okay. So the controller again is an RNN. It will generate a string. So you sample an architecture A according to that string. And then when you sample, you have some probability. And the probability is basically multiplying the tokens generated in the string. So that's probability P. And then you train the child network with that architecture A to get some accuracy R. And in our experiment, we use validation set accuracy. So we decouple. By using validation set accuracy, you can actually fold in the concept of generalization as well, which is fairly powerful. And then after we get the accuracy, we compute the gradient with respect to P, and then just scale it by R. We use policy gradient to train it. And then we update the controller parameter. And then we basically run this. In actuality, we actually every time we sample like 10 strings or something like that, right? And then we gather evidence about this 10 string, and we update the controller and so on and so forth. You have a question? Yeah.
Is the RNN conditioned on anything? So is it just generating an architecture from scratch, or are you saying for this data set, give me an architecture?
Oh, right now it's unconditional, so it doesn't have a token to represent the data set. But I guess that's just one thing you can do. So that if you want to do transfer learning, that's also beneficial, right? You have a token to represent the data set. Any question? Okay, so let me go to the part of how the controller RNN works. So the controller RNN works in the following manner. So it starts out by state of 0, nothing, and then it will try to generate one layer at a time. And the assumption is the input or the output of a particular layer will get fed into the next layer. Okay? And for each layer, for the convolutional architecture, you can think of, for example, it's going to first generate the filter height, and then generate the filter width, and then generate the strike height, strike width, and then number of filters. And then one trick that we did was basically when we make a decision, we're going to sample from it and then get feedback in as an embedding for the next step. So it's auto-regressive. Right? And any questions so far? Okay. So at the top is a softmax classifier, right? And because using the softmax classifier, you can find the probability, and then you multiply the probability of the entire softmaxes, all the softmaxes that you have, to have the probability of the string. And then we're going to train it with using reinforce. Before I told you about the reward signal R, which is the accuracy on the validation set. And then we're going to maximize, we're going to optimize for the expected accuracy on that validation set. And consider the token that we generated going to be the list of actions of the model take. And what we're going to do is basically, and then we can just take use the log derivative trick, and we get the reinforce. And basically, the way it works is that we basically compute this derivative with respect to the p of all the action, a log derivative of p of all action, and then we sum it up over time and all the in the example in the mini batch. So for example, every time you sample 10 strings, for example, in this case m is 10, you sample 10 strings, and then for you have 10 workers. Each worker will train a model to convergence, and then get some accuracy on validation set, and then you use it to scale the log derivative to update the controller. And then so this is how it works. So the controller parameters are in the parameter server. So right now we have about 10 parameter server, and then each parameter server will generate and then we have the controller replica that get the parameter from the parameter server, and we train m models each, and then each of these things will give you some gradient, and then you basically update the controller parameter, which then update the parameter server. So in our setup, we run it with 800 GPUs. So each of this GPU we basically train a model. So this is something that you basically train for like few hours to get some accuracy, and then use it to update the controller parameter. Is everything clear? No questions? Yeah, have a question.
How long does it take to train in total? So you have 800 things training in parallel. So how
Yes.
many like iterations do you need to get like decent performance or convergence?
Yeah.
Oh, yeah, so we trained for
You can use a microphone. Yeah.
Yeah, so we trained for a total of between 13,000 to 15,000 models.
Okay.
And then this total process takes about 2 to 3 weeks.
At Google.
Yeah.
Okay, you have a question?
I was curious about why you chose reinforce as the reinforcement learning algorithm. Isn't it relatively sample inefficient?
Yeah, you have a comment?
Yeah, so we kind of chose this just because it was kind of the simplest thing, and it's somewhat easier to tune than other methods such as Q-learning. And so, when we run this at such a large scale, it's hard to tune the hyperparameters a lot because we can't run that many experiments. So we kind of went with this in the beginning because it was somewhat easy to get working.
The reason why I chose to do reinforce is because that's the only reinforcement learning method that I know. So you probably know more about reinforcement learning than I do. Any question? We ran and we use this setup to run experiments for 2 types of models. The first model is to design convolutional architectures for CFA10, and the second is to design a recurrent cell for a language model task on Pantry Bank. And the summary of the result is that we achieve state-of-the-art performance on Pantry Bank datasets, and almost state-of-the-art on CFA10. We were state-of-the-art until last year someone actually make it better. And by the way, these are 2 of the most benchmark datasets, perhaps 2 of the most benchmark datasets in deep learning. So, and people have worked on these datasets for many years. The cell that we evolve on Pantry Bank actually can do transfer learning. So we can take the cell that we've evolved on Pantry Bank and use it for all the tasks, and it still works too. And we open source it as well. So if you want to use that cell, you can download it in TensorFlow, and it should work slightly better than LSTM. I will go to some of the details about it, but yeah, you have a question.
I was just wondering, so the architectures that were discovered by this architecture search method, do they bear any similarity to things that humans design? Like if you just visually look at like what does the architecture look like, how does it compare to Inception?
Right. I will go to some details about it, but on CFA10, what we found was that is indeed hard to understand, but it likes a lot of skip connections. It likes a skip connection, so that's a good sign. On pantry bank, the recurrent cells, it has some resemblance to the LSTM cell, although it does more stuff. And there's another thing that it does is that it does something similar to the attention within a cell. So I think it's interesting. But I will go to some of the details and you will see it. Yeah, you have
How
it.
did you compare to other like neural architecture search methods?
Yeah.
Need or other evolutionary strategies?
Yes. Yeah. Evolution strategies. So recently at Brain we also do have a project using evolution to come genetic programming to come up with convolutional architectures for CFA10, and that result takes longer to get and is worse than the result here.
Did you try against NEAT, neural evolutionary augmented technology?
We didn't try that. We tried something fairly basic and more scalable, but it's worse than the result we got. I think this is we also make comparison against Bayesian optimization. It's not a fair comparison though, because we have more machines, and our results are better and more scalable. And one of the reasons why more scalable is that in Bayesian optimization you have to inverse a matrix. And if it's a big matrix like 20,000 by 20,000 or so, it's kind of hard to do inversion. Whereas our method, we don't have any inversion, so it's easier to train. So there, we also, so you will see we have make some comparison in the slides. Any question? Yeah, you have a question.
So how do you initialize your model? Because I figure there's a lot of combinations that don't make any sense and probably will not lead to anything useful.
Yeah, we try to make sure that the string that you generate gonna end up to be an executable network. So the grammar always generate like a string that can construct a legitimate network.
So you have like a grammatical loss or something?
We constrain the search. We constrain the and for example, I go back to this one. This one you make sure that input at layer n minus output at layer n minus 1 is fed into layer n, so you don't have the problem of a layer that doesn't have any connection to any other layer, right? So in this scheme, that string is a legitimate string, so you can actually create a net and train it. You will see later that in another grammar, there's a problem that the string might not be a legitimate string, but we have a way to fix it. I'm gonna get to that quickly. Yeah.
And so the sequence length of the RNN is that fixed or hyperparameter? So do you generate networks of the same size every time?
Okay, I tell you what I wanted to do and what we actually did. What I wanted to do is it actually generate the termination token, which I stop. Right? But I think what happened is in practice it always favor the small network, because small network is easier to train and so on. So it always favor network. So what we did was basically train small strings first, and then make it is a number, fixed number. And then train more small string first, and then train bigger string, and then even bigger string. Yeah, you have a question.
So once you've picked a parameter and you sample a bunch of architectures,
Yeah.
you tend to just get the same architecture every time, and you're really kind of like running different random restarts, or is there a lot of variability? Like I'm just wondering what it.
At the beginning, you have a lot of variations, right? Because the net is random. So you sample a lot of architectures very differently, but then slowly at conversion, it's kind of try to zone in like an area of really promising architectures. It's a problem, and we usually add a little bit of noise to at the end, so that it doesn't converge to the it doesn't try to overfit like to that area of the search space. Any question? Okay, let me go to the. So for CFAR, this is what we do. So the first set experiment is that there's no skip connection. So we have this straightforward, and for filter height, we predict the softmax has to select between 1, 3, 5, and 7, and for filter width same, strike height is between 1, 3, 2, and 3, and then strike width same, and the number of filters is 24, 36, 48, and 64. So that's the range of values that the softmax can pick from. And we don't use continuous control. It's like a discrete. So we just select from a list. Okay. Yeah, you have a question.
Roughly, how large are the LSTM units in the RNA?
Yeah, so I think in this it was a one layer, like 128 unit RNN, so pretty small.
Did you find like that there were some trade-offs between making it bigger or smaller, or was that just the thing that you guys went with?
Yeah, we didn't try tuning this too much, but I certainly found making it bigger to do worse.
Right. So as you can see, there's some limitation to this architecture. There's no skip connection, right? And neural net, the convolutional neural architecture these days, people tend to have a lot of skip connection, like the ResNet and the DenseNet and so on. So we actually extend our scheme so that we have residual connections and branching and skip connections and so on. And the way it works is the following. So at every layer, we also predict like we have an anchor point prediction. And this anchor point prediction, we select from the previous layer how many layers we want the input from. So, so for example, here, the way it's selected is that layer J is an input to our layer I, is a sigmoid function that way. And basically, this is also, you can actually backpropagate and train V and train W as well. And then what we do is that let's suppose that the string is generated, and at layer n we have connectivity to layer n-1 and then maybe layer 3, for example. What we do is we take layer n-1 and layer 3, concatenate them together, and use it as input to layer n. So and if at the end, if a layer doesn't connect to anything, we actually hook it up to the softmax, so that you don't have a layer that have no connectivity, like a dangling pointer, right? And this is the way to actually have a scheme so that you can end up with a lot of branching and skip connections. Now the connectivity that we have is not strictly residual connection, because in residual connection you have identity connection, but in our scheme we treat them as input to the next layer. So we concatenate all of them and then send it to the next layer. Is that clear or is it not clear?
One thing I didn't get,
Yeah?
One thing I didn't get is that the anchor point that's being generated as part of this sequential process, is that a decision that this network is making? And if so, what's the symbol that's output there?
It's gonna output a list. It's gonna output a list of layers that input to this n layer.
Yeah.
So it output like a list, right? Because this would say you can sample from it. This is a probability. It says layer J is an input to layer I. It's a bunch of sigmoids. So you can sample from it. And once you sample, you have either on, 0 or non-zero. And it's 1, that means there's a connectivity.
That makes sense.
Yeah. And then that's another probability that if we're going to end up like multiplying in our string too. You have a question?
Question. How well do you think this would scale to larger image data sets, like image in Pascal?
I think we're gonna have a problem because we have 800 GPUs for CFA. So I think hopefully when computers are getting fast quickly, right? That's one thing that we know, right? 10 years is gonna be 1,000 times faster. So don't worry about being slow. that's what I say. Yeah, Moore's law is actually very powerful. So if you start now, like in 10 years, you are 1,000 times faster. So any question? Okay. Some more details. So we use 100 controller replicas, and for each replica we train 8 chai networks. So in total we use 800 chai models. So each model corresponds to 1 GPU. The reward given to the controller is the maximum validation accuracy of the last 5 epochs and then square. Because it trying to encourage kind of some sort of stability. And then CFA has 50,000 training examples, and then we split it so that we have 45,000 for training and 5,000 for validation. Right? The R is computed on these 5,000 examples. And each chai model, after it's generated, we train for 50 epochs. And how long does it usually take? 50 epochs on CFA?
Oh, I don't remember exactly off the top of my head.
A few hours?
Yeah, maybe like half a day.
Half a day.
Half a day.
So each of the so is it like gradient descent, but it's like every iteration of gradient descent take half a day. And then the total number of chai models that we trained was about 12,800. And we use curriculum training for the controller by gradually increasing the number of layer samples. So we start with small number of layers, and then we increase and increase so that it will we encourage deeper and deeper networks. Have any question? Okay, you have a question.
I guess if you have a budget of 13,000 models, you can run a pretty big grid search over parameters too. Do you have a sense of like how much of the
search space is very large.
Search space you end up exploring?
The search space is very large. You can use a microphone.
Yeah, so the total amount of things that could be tried is pretty massive, like 10 to the 30, 10 to the 40.
Yeah, but like if you sat down a researcher and said, what parameters would you try if you could only try 13,000 times? They would probably pick some set that's smaller than 10.
Yes. Humans are always better. Are currently better. I agree.
Well, maybe not, because you're like getting state of the art, so it's excellent. I'm just wondering, like, whether.
Well, we humans don't need 13,000 models, that's for sure. And then somehow they manage to get to a very good position in search space very quickly. That's what we know. What else? I think if you do random search, you should not be able to get the results in the paper. You're probably a lot worse, I think. Yeah. Because there's also Bayesian optimization that we compare against too. Yeah. So here's the result. I think. Okay. So so this is error rate. I think. So this is error rate. So the best model that we got is about 3.65 error on the test set. The best model is I think here is 3.46, which is the dense net. And in the dense net, what they have is a huge deep net, and then they connect every layer to all the layers. And the net that the model, the controller generated looks something like this. If you're curious, it's like something like this. So you see, there's a lot of skip connection that it likes to do. Right. So in that sense, one thing that is also like is a lot of rectangular filters. So it's like 7x4 filters kind of models for some reason. Okay, so the Bayesian scalable Bayesian optimization method is at 6.37%, and there's actually trying to get past 4% is actually really hard. Because yeah. Now I also there's also a result for evolution. They get 5.4%. And then the concurrent to our paper, there's also the Q method using Q-learning, and they got 6.9%. Anyway, yeah, have a question.
So I have trouble with these validation results because you're kind of doing a problem on, like, you're trying to validate your search algorithm on one particular data set that you're searching on, right? It's not conditioned on anything, but in some sense, you're only working on one data set.
Yes, that's right.
And even if you did like 3 or 4, you're still not doing I don't know, in my mind, a just validation of the search algorithm.
Right.
How do you, like, do you have any comments on that, and how do you?
Well, I think number one, sometimes one data set itself is valuable enough that spending a lot of effort on it is worthwhile. For example, thinking about cancer images, right? If you can actually get really good performance on cancer images data set itself, that's already valuable. Or self-driving car, for example. There's enough value in the data set that I think getting better accuracy for that particular data set is important. I think in the future, if you want to, I think there's some value in doing transfer learning. Namely, you have some kind of representation of the data set, so that once a new data set comes in, right, it uses information of the previous task and generate a string immediately that is good for that data set. I think that's the ongoing work, I guess, of trying to take this technology and make it more generable to new data sets by doing transfer learning. I think that's a promising direction. And it's possible to do by basically having some way to condition on the information of the data set. So right now, the recurrent network, right, doesn't read any information about the data set itself. You should give it more tokens about the data set. And then it should, based on that, generate you initial strings that are good. Yeah.
There's something kind of funny here because there are actually two decisions, right? There's the algorithm you use, whether it's Bayesian optimization, policy gradient, etc., and there's how you represent your distribution.
Right.
So you can choose to parameterize, like essentially you have a big discrete distribution over this giant joint thing.
Yeah.
And you can choose to parameterize it with an RNN the way that you did. You can also choose to just directly have like a bunch of independent, multinomials for all these variables.
Yes.
That maybe is a little bit naive. You could do something more sophisticated, like you can have like an autoregressive thing where you just have without any hidden units. So you can just have like the probability of your filter size given the previous filter size.
Yes.
And that's just a little CPD.
Yeah.
I wonder if you have any thoughts about whether certain algorithms go with certain representations, or whether we should decouple the distribution representation from the algorithm and evaluate them separately, or because it feels like in this evaluation these things are kind of being confounded.
Yeah, right. I think when we first tried to do this, our goal was to say that it's trying to make it possible, right? Like trying to do the best we can. But there's a lot of scientific comparisons that one can do. For example, what you said, right? Can we just not use a recurrent network, but like a lot of like small classifier to do this, right? I think having the recurrent network has a lot of values because it can generate variable length strings, and that's what I like. Right now, it doesn't, like in the actual implementation, we didn't have this like M of sequence token that I wanted to have. because of it prefers shorter strings. So that's why that the curriculum training. But I think that's the place that we want to get to. I think when we get to that, then everything is automatic, right? It's basically generating variable length strings. Yes. Have a question?
So is the depth of the network that it picked the maximum depth that it was allowed to pick, or did it decide to make a?
No, yeah, so that was the depth of the network shown there is the maximum depth that we allowed it to search over.
Yeah. So we have a maximum number, and then it allows it to search
That was
over.
the way to go.
Yeah.
Did you
Yeah.
consider making your RNN kind of like a Turing machine that traverses a graph? So instead of like specifying a long string, you could specify like a neural network whose actions are to produce a new node on the graph and make a new connection on the graph, and then within the graph produce a string that says, okay, this is a 5x5 com filter, or this is an LSTM unit, and build a computation graph that way. So it seems like you're forcing in these skip connections as like a string, but you can't hope to ever have much more complex graphs, like you would see inside of something like Inception.
Oh, this can generate inception, because you inception by itself you can generate like the architecture can be described by a string, right?
Sure. I don't doubt that it can generate it, but it's very biased.
I see.
Towards architectures that look like this, just given the way you're outputting these strings and the
Right,
density of
yeah.
the anchor points in strings. So
I think that's a good idea. I think that can be a good next step. Is trying to actually not only doing like a straightforward string, but like make it into a graph. Again, this is like the very first attempt in this area, right? So we welcome more contributions, so that like make it more the framework more flexible and so. That's true. Yeah, you can do an internship at Google. Any question? Yeah, I think the only better result that that in this table is basically by Huang et al. Very much recently, like a few months ago, right? Yeah, and that result beat our result. Yeah.
So can you talk a little more about the findings that the algorithm output? So you already talked, there's a lot of skip connections.
Yeah.
There seems to be rectangular filters.
Yeah.
Which I've not heard before. What
Yeah.
other things are there?
What other things that we learn?
Yeah, so there were certainly the rectangular filters, the fact that it likes to have a lot of these skip connections. And another interesting thing that we noticed is that it likes to connect the first layer after the first convolution to almost all the other layers. So I'd say those are the three biggest things we noticed. But yeah, certainly some of the things are hard to interpret, and we haven't spent a lot of time trying to really analyze what's going on with it.
Cool. Yeah, I have a
Is there
question.
some way that we could understand just how much it changes over the course of the optimization? Like if you take, 10 random RNNs, generate networks of comparable length from
Yeah.
those RNNs, will they look very different from the one that you actually get a convergence?
Right. We haven't done that experiment. One thing that I also wanted to do as well, I think that's a great experiment. The one thing I wanted to do is that look at the string towards convergence and see, you visualize that string, right? And see what kind of things that it likes to keep going, and then what kind of changes it's trying to adjust. I think that would be very informative.
That would answer basically the question about whether there's bias introduced from your particular choice of parameterization.
Yeah.
I mean, maybe there is bias introduced, but maybe it's actually not favorable bias. Maybe it's actually the learning process that does the whole thing.
Right. Yeah. So the second set of experiments, we want to generate a recurrent cell. So how do we do this? So if you look at an LSTM cell, so our search space is actually based on the concept of the LSTM cell. And how does an LSTM cell work? So an LSTM cell works is basically you take the input of the current step, the hidden state and the memory of the previous step, and then you create a computational graph so that you can arrive at the hidden state of the next step, and the memory cell at the next step. Does that make sense? And the way it works is that you take the hidden state at the input, you take a W matrix multiplied by X, W time matrix time multiplied by H, sum it up and add, and apply a sigmoid, and then you take these two, apply a tanh, and then apply element multiplication. And most of the dot product are in these 4 adds right here. The rest is basically element-wise dot product or element-wise activation function or multiplication. And then this graph will give rise to the hidden state and the memory. So we were inspired by that idea, and what we wanted to do is so this is complicated. So this is really complicated, but I want to explain it. So the idea is basically you want to take that computational graph can be thought of as a tree of computation, and you take let's say here you have a tree of 2 nodes, and you want to take xt and ht minus 1, and you want to decide what activation function or what combination method you want to use for them. So in the LSTM cell, that's an add function, right? So you want to construct that tree, and then you use your controller INN to loop over that tree to label what function you use to combine or activation function that you use for it. And then once you generate that tree, you can actually map that into an actual implementation of the cell. Right? So you loop over that node in the tree, and then you know that, oh, in that way, let's suppose that it generates addition in the first step. So you can take xt, add with ht. And then let's say that the second step, it will do tanh. That means you apply tanh at the activation function at that step. So the job of the controller INN is to loop over the tree and then generate what function it has to choose from.
So the tree is fixed shape?
Yeah, if tree is fixed shape.
And it's the same shape as the LSTM tree?
Bigger than the LSTM tree. So right now, in this example, I only see a tree of 3 internal nodes, and the base is 2. The base is 2, but like in our implementation is a base of 6 or a base of 8. So the tree is 8. The leaf nodes of the tree is 8. So here we have only 2, but in our experiment we deal with 8. And so the data set that we run is the Pantry Bank language model data set. Again, we use a base of 8. We use 400 controller replicas. Each replica trained in 1 child network. So, and we use CPUs for this. So we have 400 CPUs. And we train 400 CPUs concurrently. And the total number of child models at the end is 15,000. The search space is much bigger, by the way, much like 10 to the 16 or something?
Yeah, I think 10 to the 18.
10 to the 18. But we only need 15,000 models to get good results. And then the reward of the controller is some constant divided by the validation accuracy, validation perplexity square. So to contrast the state of the art. So in the LSTM cell looks this way. So I already explained it. The cell that we generated, it looks a little bit more complicated because we have the base of 8. So 1, 2, 3, 4, 5, 6, 7, 8. It's a base of 8. And then that's the best cell that it found. Yes?
There's no skipping connections in this
no skip connection. So it's a fixed tree. You just basically go through, and then this structure is fixed. You just need to go through and then label how what combination method you use and what activation function to use. And there's a degree of freedom is where to hook the memory cell, which node in the tree to hook the memory cell to. That's it. The CT, there's a degree of freedom where you want to, which node in the tree you want to hook it to. Yes?
So it's doing some really strange things. Like it has a ReLU and a sigmoid, and they're pointwise multiplied, and has a sigmoid and a tan H, and they're pointwise multiplied.
Yes.
Do you have any thoughts about why it wants to pointwise multiply different nonlinearities like that? That's
Right.
interesting.
So the base, except for this thing, right? Except for this thing, the base looks very similar to the LSTM cell. So it prefer adding things up. But there's this thing that is actually trying to multiply these two things together. So what it amounts to, in my opinion, is basically take the hidden state in the previous step and trying to multiply them up to the current state.
So that's what you refer to as kind of being almost attentional.
Yes, yes, that's it. It's just marvelous that it invented such a cell. And this is open source. So a lot of people, some people already tried it internally at Google for several other problems rather than language model, and they got good results, better result than LSTM using this cell too. And more concretely, here we have some results. So this is Planetary Bank dataset that many people have benchmarked. They are recurrent networks in LSTM and many methods to do language modeling. Thomas Mikolov is one of the first people who did it here in 2012. I still remember I worked on this dataset in 2014, and when I got perplexity of about 90, I got really happy. 90 perplexity, and now like I was basically like super happy to get 90, and now we got 60. It's unbelievable. And we actually usually when people get gains, they get like one or two perplexity, but we got like 4 perplexity gain right here using this method. Yeah, I have a question.
I'm not really familiar with language models, so how do you define perplexity?
So you look at the softmax. So you predict the next word using a softmax. That's a cross entropy loss, right? Exponent of that is the perplexity. Yeah. So in language model, these usually high. In translation, you have it's a conditional language model. Where I haven't talked about it, but like usually you get a much lower perplexity. But this is usually the range of perplexity that you get in. If you try to predict the next word in a sentence. Yeah. Any question? All right.
Wait, so which two numbers?
Yes.
Is it fair to compare this to the LSTM medium line?
The number of parameters is the same. So it's the constraint that we want to have is they take the same amount of time to do inference.
Yeah.
And it's the same amount of cost. For example, this model and this model, same size. This model and this model, same size.
But I feel like everything below the LSTM medium, which is like one of the early.
Yeah. Yeah, I
is
mean
doing
this
more than just.
this is 66 million, right? This is using LSTM.
Yeah. But these are all doing like other tricks too, right?
Sure. I think this, for example, we don't use this trick. This trick is called the pointer sentinel trick.
Yeah.
We didn't use this trick.
We're not using character CCN trick either.
Yeah, we didn't use character.
It just seems like we're getting a lot
Yeah.
of benefit over the LSTM.
Yeah.
Not just going from 66 to 64, but going from like 70.
Yeah, I think the
82 to 64.
yeah a valid comparison could be from here, like this one and this one, right? Got it?
Yeah.
I think a good comparison would be that one, about 68, and that one, which is 78. So that's a benefit of 10 perplexity.
Well, I think John's question was which one is sort of like, if you just want to compare, is your cell better than the
Yes,
LSTM
that's-
cell? Which
yeah.
one is the fair comparison? Is it the LSTM large or the LSTM medium from Wojciech's paper?
No, it's the variational LSTM because that's the same regularization we use.
Yeah.
We
Oh, I
just
see.
use their regularization
Okay,
stuff.
got it.
So basically
Yeah.
everything they do, we just replace the cell. For the ones with no shared embeddings. With shared embeddings,
So
other
it's
stuff.
yeah, I think the best comparison would be this one and one of these two, right? This is 32. This
Yeah,
is
we don't
30
use
million,
the MC thing. So
and
the
this
one
is
above.
66 million. So it's fine to compare this one and that one, right? Any question? Okay. So one baseline that we compare against in this model is random search. Apparently, random search is actually a hard baseline. We look at the difference between the best of our model and the best of random search model, and then we plot over time. For example, if you look at the top 15 best model, and in our case, the average of top 15 minus the average of top 15 of random search, you're a lot better. If you take so the best models of the top 10 best models that we have is usually a lot better than the top 10 models of random search. If you only take the best model of random search and the best model of owl, the gap is smaller, but there's still a gap, and it's still increasing, I think. So, any question?
Well, does that, I mean, the fact that the top one is like a lot closer to random search, doesn't that just say that random search is, the density of random search is very even, and then your search is biased towards the best results?
Yeah.
In other words, that I mean, like, because that complexity difference isn't that much. So, are you that far away from random search in your mind? Like,
Yeah, okay.
Well, I think 10 perplexity is a pretty big difference.
Is a big one, yeah.
Yeah, so I think that's it's pretty significant.
We also took the cell, and then instead of doing a world level language model, we do character language model, and we also beat existing state-of-the-art result as well. And this illustrates the aspect of transfer learning. So the architecture that we found on one task actually works well on the other task. We also apply the cell into something called the Google Neural Machine Translation. So if you use translation today, you interact with this system. And they use an LSTM cell in the system. And then we basically, and they tune a lot of things. So they tune the learning rate, they tune the how the gradient clipping and so on in the network. What we did was basically take our cell and drop it in and replace it and change nothing else. And we got a boost of 0.5 blue score improvement. And 0.5 is in the range of significant improvement.
It's about the same speed.
Same speed.
Yeah.
Because we control, there's the production constraint in speed, and we make sure that it's the same speed. So the cell, people have tried this on other domains as well, and it also works. So there's something about this cell that is actually interesting that we need to analyze it.
So are you guys doing the architecture search on the data set that's used for this system as well?
Oh, that would be hard because this model would take
But if it's a production system, then
Yeah. Each of these.
What's a few months in exchange for a few million?
Yeah, yeah. This model itself takes like a week to train. So if we train like 15 on 96 GPUs, this one takes a week to train on 96 GPUs. So the Google Translate system that you use is this one right here. And if we want to do architecture search on that, I think it might take a long time. So transfer learning is more possible now. Any question? Yeah.
So in these sequence models, we've always used the same architecture for every position in the sequence, and that always seems strange to me because the beginning's different than the rest.
Yeah.
So it seems like you could use this architecture search to figure out whether it's a good idea to have like a different architecture
Indeed, yeah.
for the first one or the first two or something.
Indeed, yeah, I agree.
That could be cool.
Yeah, I think it allows us to do some combination of new ideas, right? Because sometimes you have a new idea, you don't know where to put it and how you do it. So this search can allow you that flexibility if you have enough compute. With that, I'm gonna pass to Barrett. And by the way, this is new. You are the first people to see the results in this presentation outside of Google. So Barrett, you're gonna do it. Okay.
Okay. Yeah. So the idea behind this was that our
Can we stick that mic?
Yeah, maybe
Yeah.
maybe
Yeah,
you can
let's-
put that on
let's-
so you don't have to hold the.
yeah, that'd be nice. Okay. Is this good? Is on? Okay. Yeah. So the motivation behind the first part was that architectures, are very hard to design, and a lot of people spend a lot of time, hand tuning them and hand engineering them to get them to work well. And another, aspect of deep learning that a lot of work goes into is designing optimizers. So there's many different optimizers that exist, such as SGD, Momentum, Atom, RMS Prop. There's a lot more, there's frequently new ones coming out. So our idea is that we want to apply our previous approach to now search over optimizers instead of architectures. So we will fix some neural network architecture in some data set, and then we will specify some string that corresponds to some neural network optimizer and run it and train it, and then depending on how well it does, update the controller RNN that sampled the string that corresponded to this optimizer. Okay. So this photo looks somewhat similar to the one for generating architectures, where we have the controller RNN, and it will sample some update rule, and then we will train for some fixed neural network in some data set, this update rule, to get some accuracy R on a held out validation set like we did before. And then we use this to then update the controller RNN with the hope of sampling better and better optimizers over time, where before the hope was to sample better and better architectures over time. Okay. And okay, so this is one way to view the Atom optimizer. So this is a pretty famous neural network optimizer that a lot of people use. And so this is one way we can view the computation Atom does for a gradient update, where it has a running second moment of the gradient, and it square roots this. And then we can also feed in a constant and pass it through an identity and multiply them. And then we can feed that in, and we can take a running mean of the gradient and then divide that with the output from the first step. So this is one way to view like all the computation Atom does. And this kind of diagram is the inspiration for the kind of configuration strings we design that we're going to have the controller RNN predict. Okay. Yeah. And then we can see that we can view a lot of other of the famous optimizers in this space. So yeah, this is the kind of inspiration we took for designing the space that we were going to have this controller RNN predict. Oh, yeah.
Wait, is the identity there? Does they all have the same shape?
The identity, no, so each of these would just be like an individual element because all these operations are done element-wise on all of the different gradients. So the identity is just there so we can view the computation from all these different optimizers in the same way. So for example, if we wanted to just use the gradient and not do anything to it, we need to have the identity there as opposed to square rooting it or something like that. If that makes sense, yeah. So this is just there as a simple way for us to not have to apply any operation to the thing we're getting passed in. So it kind of makes it like a more flexible space. And so this is how we have our controller RNN predict these different optimizers. So at the first time step, it'll predict some operand, which could be, for example, the gradient, moving average of the gradient, and moving average of the second order of the gradient, and various different components that a lot of these other famous optimizers use. Then it will also predict a second operand, and then it will predict a function to apply to the first operand. So for example, it could do an identity, a square root, raise it to some power, take the sign of it, for example. Then it will also apply another function to the second argument. And then we predict an operation to combine the two outputs of these functions. So for example, it could add them, element-wise multiply, divide, various things like this. And so yeah, we took inspiration from a lot of the other famous optimizers for like what different things we wanted to allow it to select. So for the various operands we predict, so in the beginning we predict two different ones, we allow it to predict things like the gradient squared, the gradient cubed, a bias corrected moving average of the various different gradients, the sign of the gradient, the sign of the moving average of the gradient. We could give it a constant. We give it also noise, like a annealed noise. We give it information about the weight. We also give it as input other famous optimizers such as Atom, RMS prop, and we also give it access to where in the training epoch it is, so you could learn things like cyclical learning rates and things like this. And then for the various functions that get applied to each of these, we allow it to do like an exponentiation, a log, a square root, clipping, dropping out some value. And then for the operations that combine the two together, we allow it to do things like addition, subtraction, division, max, min, and things like this. Yeah, that's kind of blurry. So yeah, we run this search like we did before on a small CFAR10 model. We do it on a 2-layer convolutional neural network, and we train for some fixed number of epochs. And so we'll search for an we'll like sample an optimizer, we'll run it, and then according to how well it does in the validation set, we'll update the controller RNN. And so then we can see here for like a famous CFAR10 model, we use this famous wide ResNet model to evaluate all of these. So this model that we're evaluating on is different than the one we're actually training on. So this is like a generalization performance. And we compare against a lot of the other famous optimizers like SGD, Momentum, Atom, RMS prop. And we show the final validation accuracy, the final test accuracy, the best validation, the best test. And this wide ResNet architecture was like highly tuned for the Momentum optimizer. And so we compare a lot of the other best optimizers we found against the Momentum optimizer here. And yeah, I don't know how well you can see some of these, but it actually learns to do really funky things. So for example, one of the really interesting things it learns how to do is it will take the gradient and it will element-wise multiply. So it'll take the sign of the gradient and the sign of the moving average, and it'll multiply those two signs together and then raise this to, so it'll be e to that value, and then multiply by the gradient. So essentially what this is saying is if the sign of the gradient matches the sign of the moving average, scale the gradient by e. If they don't match, then scale it by 1 over e. So essentially if it's more confident, then it takes larger jumps. So this is one of the really interesting things it learns. And we see here that it actually does about one test percent accuracy better than the wide ResNet model, which was actually tuned for the Momentum optimizer, which is pretty interesting. And so, yeah, we wanted to experiment more with this kind of interesting update rule that we found. And so one of the things we did was we applied it to this, very common like optimization test with this Rosenbrock function, which is it kind of has this one like valley, and then it has to find the local minima, which it has to kind of traverse along this small valley. And So we compared this against a lot of the other famous optimizers just to see how well this optimizer we found on CFAR 10 does on this kind of standard stochastic optimization test. And we can see the optimizer _1 is the optimizer I showed before. And it actually reaches there faster than any of the other optimization methods besides momentum on this. So this was pretty promising. Okay. And so another thing we wanted to do is test how well this generalizes to like another famous deep learning data set. So we used the Google neural production translation system that was very tuned for the Atom optimizer. And all we did was we just simply swapped out the Atom optimizer for this, and we get a 0.5 blue point improvement, which is promising. And we also get a better training perplexity to show that this thing is actually doing better optimization. Yeah.
So in the original GNMT paper, they said they ran Atom for a while, and then they ran SGD for a while after that.
Yeah.
Is this kind of like switching your optimizer within your space of options?
Sorry, do you mean?
In our experiment, we only use Atom, and then we compare it with the new update. We don't do this switching update. It turns out that switching update only improves just a little bit.
Okay, it'd be great to get rid of that. So maybe
Yeah. Mm-hmm. And yeah, I think that's it. Any questions?
So there's kind of this trade-off that you can make between whether you want a more general optimizer for like this really big transfer from one architecture to a completely different one versus sort of like an architecture-specific optimizer. You can imagine maybe for some particular problem, maybe it's better to optimize the convolutional layers using one scheme and the fully connected layers using another scheme or something like that. Have you looked into kind of this, basically combining architecture and optimizer?
No, so yeah, so this is still preliminary, and there's definitely a lot of interesting things to try. But one thing we did try in this is we do give it access to weight information. So in some sense, it kind of could know some things about the architecture based on, if there's certain different architectures that have different distributions of weights. It could learn to do interesting things with that.
So the weights are fed into the RNN that generates the update rule?
No, so the weight is one of the operands it could have access to, so it could use that in the.
Have you tried learning the optimizer in a symbol-free way? So you just try and learn a neural network that takes in G and the momentum and then predicts the proper output, the proper gradient.
Oh, yeah. So this is very similar to the learning to learn by gradient descent by gradient. Yeah. So no, we didn't do that. But one of the benefits we see of this approach is that we just produce only an equation. So it's very simple. So for example, it's very easy for anyone to use this on a new problem because now it just becomes like another TensorFlow optimizer that doesn't need to be trained or anything like that.
Okay. And then follow-up question: there's work a while back where they had a bunch of like physical experiment data, and they had a system that used evolutionary strategies to predict F equals ma. You tried or thought about even touching that domain?
Yeah, we haven't done anything like that, but that is very interesting.
So I guess this update's kind of complicated because it's like very nonlinear. But have you thought about like how this behaves for convex functions? Like, I mean, it's very easy to show things like gradient descent will converge under some conditions. Have you guys thought at all about like even for a very simple case like a quadratic, like can you guarantee convergence with some step size?
We haven't thought about this, but that is interesting.
This is just a form of momentum, right? Because you just basically check the sign of the gradient.
And if you're moving in the same direction, you keep moving.
So I think you could prove it. That's my gut feeling, but yeah, I don't.
Yeah, it's just that the way it's combined is a little bit complicated because in momentum, the nice thing is it's like a linear sort of combination, and here you're taking the sign of the moving average, which updates your map. So it just the intuition is that like I think is the same. But I'm just wondering if even for quadratic, it comes in a sort of a nonlinear way, but it might be an interesting problem. Yeah.
I was very surprised that it came up with something very simple like that, and I did not think of it before.
Yeah. Is the just one more question? Is the base important? Like the scaling doesn't really matter, right? E was just like something symbolic grammar.
Yeah, exactly. So I didn't try playing around with this too much, but on one of the CFAR models, I tried tuning it and found it was somewhat insensitive to this.
Okay, so that really doesn't matter.
Yeah.
So for people without like 800 GPUs, it would be nice if this thing converged fast too. So maybe there's an opportunity to put in your reward, not just the final accuracy, but how fast it got there.
Yeah, so this is something certainly you could put in there. Yeah, because it's very flexible when you're using reinforcement learning because you can kind of just shape the reward to however you want it. So it leads to a lot of really interesting things like this.
Yeah, the nice thing about the optimizer search is that it was done in a smaller setting. The network doesn't have to be small. So when we train the controller to find the optimizer, it's actually ran in all. The try model was actually a 2-layer ConvNet, which was very fast to train.
Any other questions?
Cool.
Well, see you all on Monday for Professor Peter Beal's lecture, and until next time. Thank you guys very much. That was pretty cool. I think you can. I bet you can easily show convergence to this thing just because it's going to be gradient.